When is extreme too extreme? Hi, welcome to PyGotham. I'm Jorn Mossel, and in this presentation I want to talk about how we can model extreme weather events using PyMC in a Bayesian approach. So the last couple of years we saw quite a few headlines in the media about extreme weather events, breaking temperature records, historical droughts, Hurricane Ida that led to many floods in New York, and so on. It's Hurricane Ida I want to focus on because that's the one I experienced myself, which happened 2 years ago. So as a result of the hurricane, there was a historic rainfall which led to flash floods, and that resulted in many casualties. So when such a thing happens, it's a natural question to ask is, how extreme is this? Will we likely see more of this in the near future, or is this maybe a once in 100-year event? So focusing in on the rainfall observations of a nearby airport at Newark, which broke the record after Hurricane Ida with 8.4 inches. The previous record dates from 1977 with only 6.7 inches. So the record was completely shattered. The question now is, how extreme is this? Or maybe actually a better question is, how often do we expect this to happen? So you could ask, like, how often do we expect 6 or more inches to happen? Or how often do we expect the 8.4 inches to happen? So in order to answer these questions, you may wonder, like, do you need a really long history here? I have here only 50 years of data. Well, not necessarily. If you know the probability distribution that describes the rainfall, you can fit that, and then you can use that to answer these questions. Then the question is, like, okay, but what distribution should we fit? Well, this is where extreme value theory comes in. So if we look on the graph on the left, we see the daily rainfall observations, but I highlighted the annual extremes. If we actually only keep these extremes and throw away everything else, we end up with the graph on the right. So while the probability distribution for the left graph is typically very complicated and often unknown, on the right hand, that can be described with an extreme value distribution. So why is that? So extreme value theory states that if you have a probability distribution that describes the maxima, like the annual observations in our case, it can be approximated with a distribution of this form. And the remarkable thing is that regardless of what the underlying process is, so that can be record rainfall, temperature extremes, or stock market crashes, etc., if you focus on the extremes, they will all follow this distribution under certain assumptions. So all we need to do is just fit the distribution. So that means we need to estimate what the three parameters, mu, sigma, and xi are. Mu, sigma are location scale parameter, and xi is indication for how tailless a distribution is. The bigger, the more extreme events you can expect. All right, how can we do this in PyMC? So PyMC, we want to take a Bayesian approach. So we start with Bayes' rule. So we say we have a posterior distribution on the left, which is proportional to a likelihood and a prior distribution. To code this up, it's actually only a couple of lines in PyMC. This is pretty much all you need. So let's break this down. So we start with a prior distribution, and that basically tells us what the belief is, what these parameters are. So we make them weakly informative. So that basically is we have some indication what the range could be, but we want to let the data speak for itself. Then we have the likelihood function that basically tells us what process generates the data. So in this case, we chose the extreme value distribution, which we discussed on the previous slide. And then all we need to do is Monte Carlo sample to get the posterior distribution And on the right, I've shown the results for the parameters, mu, psi, and sigma. And that's basically our estimate for the parameters. So let's talk about return levels, which is the graph on the right, which I will explain step by step. So we first need to pick a return period. So that can say every 20 years or 40 years and so on. And then the return level is the level which we expect to observe or exceed for that return period. So if we look at the graph, so every 20 years we expect to see 6 inches or more. And every 40 years we expect to see 7 and a bit inches or more, and so on. So after we fit the distribution, to actually compute this, is only a few of additional lines. So we use the fitted results and plug that in the formula for the return level, and there we go. So back to the record that we observed in Newark in 2021. So according to this graph, the 8.4 inches corresponds to a return level of 83 years. So that means every 83 years we expect to happen something, what happened during Hurricane Ida. That's one, but there's more in this graph. So one of the advantages of using a Bayesian approach, we almost get for free a measurement of how uncertain we are of our predictions. So that's basically the blue area behind the graph. And as you can see, there's quite some uncertainty. So if we look at the 83 year period, the range is actually from 6 to almost, to over 11 inches. So that's quite a wide range. So we actually don't have a very precise prediction of what we expect to happen every 83 years. So how can we improve this? You may think just add more data by adding a longer history. Often this is not available, or it's not even appropriate to use it. If 100 years ago the weather was very different than now, that doesn't help us to make predictions for what we can expect in the near future. So what can we do instead? Instead of looking at one weather station, we can look at many weather stations. So here on the map, I highlighted Newark in red, but then we have loads of other stations for which we can use their data as well. But we have to be slightly careful here, because we know it can vary from station to station. But we expect stations that are close to each other, we expect we will observe something very similar, and the further apart we go, it can be more different. So how can we model this in a Bayesian way? Well, if you remember, initially we had the prior, so that was our initial belief of what these parameters could be. But that focused only on one station, but we can now change that prior with the so-called Gaussian process, so we can actually incorporate information from all the other stations as well. And we did it exactly in the way we described. The Gaussian process basically puts more weight on stations that are nearby for the station you want to make a prediction, and then for stations further apart, they influence less that prediction. So I went ahead and I coded up the Gaussian process. Slightly more work, but hey, it still fits on the screen. And here we go. So let's look at the results. So we have the graph in blue. Those were original predictions. And now in orange, that is the new prediction where we incorporate the many stations with the Gaussian process. So we see two things. The orange line is now slightly lower, but B, more importantly, the uncertainty band is almost twice as small. So we made much more accurate predictions. So what we happened in Hurricane Ida, actually now if we look where it intersects the orange line, it became a once in a 100-year event. And now the range is only from 7 to 10 inches. So back to the very first question. Is this extreme or is this too extreme? Well, first I want to say this is only a toy model, obviously, with the purpose of demonstrating how you can model this in PyMC. To make more rigorous statements, you need a more complex model. But a once-in-a-100-year event is definitely something extreme. And but is it too extreme? Well, our model is still not super precise, so we don't have enough evidence to claim that something else is going on. Thanks for attending. Please visit my GitHub for more information.